What happens when metals are burnt in air? When most metals are burnt in air, they combine with oxygen in the air and form metal oxides. Example, sodium. Sodium is Na. When it is burnt in air, it will combine with oxygen and form sodium oxide. Here is where the equation is balanced. This is sodium. When burnt in air, it forms sodium oxide. Same if you take potassium. Potassium is K, and when it burns in air, it will combine with oxygen from the air and form potassium oxide. Magnesium too. Magnesium is Mg. Mg, when burnt in air, it combines with oxygen and form magnesium oxide. This is magnesium. Magnesium may be a magnesium ribbon, and this is magnesium oxide, which is like a white powder. If you take up copper, will also burn in air, combine with oxygen from the air and form copper oxide. This is copper, and here we have copper oxide. And remember that copper oxide is black in color. You need to balance the equations. For example, here you'll have to balance it. So in short now, when metals react in air, they give you metal oxides. When aluminium, Al, reacts with air or is burnt in air or is heated, it gives you aluminium oxide. Aluminium is a solid, oxygen is gas, aluminium oxide is a solid. That's aluminium, and here is aluminium oxide. If you were to balance this equation, you would have put here 3 oxygen, this would go 2, so it becomes 6, and here you would put 4. To take more examples, zinc, a metal, combines with oxygen when burnt and to give you zinc oxide. Zinc is solid, oxygen is a gas, and this too is a solid. So you have zinc on burning with air gives you zinc oxide. But there are some metals like gold. You take silver. They do not react with oxygen, even at high temperatures. They do not combine with oxygen at all. So they are very unreactive metals. And that's the reason why here I wrote most metals react with oxygen. The exception to this is silver and gold. They do not react with oxygen even at high temperatures. The next we are going to see the nature of metallic oxide. We are going to find out, are metallic oxide acidic in nature or are they basic in nature? So we take some metallic oxides and we dissolve them in water. Not all metallic oxides don't dissolve in water. Some metallic oxides you dissolve in water, and when you dissolve them in water, you get hydroxides. And these hydroxides, which are soluble in water, are called alkalis. Like if you take the example of sodium, you have sodium oxide, and when sodium oxide is reacted with water, it dissolves and forms sodium hydroxide. Now the sodium hydroxide is an alkali because it dissolves in water. And an interesting thing is, if you put red litmus, it turns blue. So you find that in this solution, if you have a red litmus paper, and this red litmus will turn blue. So what can you conclude about the nature of this alkali? It must be basic in nature, because the red litmus has turned blue. However, if you add blue litmus to an alkali, it will remain blue. So a blue litmus added in an alkali will remain blue because it is basic in nature. Same thing if you take potassium oxide and you add it to water, it dissolves, so we'll get an alkali, and that alkali is sodium hydroxide. Now why do we call it an alkali? Because it dissolves in water. So this is sodium oxide, which is a solid. You dissolve in water, which is a liquid, and you get sodium hydroxide. And since it dissolves in water, we put it AQ. It is an alkali. So here we have seen that sodium oxide and potassium oxide dissolve in water to form alkalis. All metal oxides do not dissolve in water. Most metal oxides are insoluble in water. Some of these dissolve in water to form alkalis. So what are alkalis? Alkalis are metal oxides that are soluble in water. And the example of alkalis we have said is sodium hydroxide and potassium hydroxide. These are alkalis that dissolve in water. If we take magnesium oxide and dissolve in water, we get magnesium hydroxide. Magnesium oxide, we here get magnesium hydroxide. Now, magnesium hydroxide is partially soluble in water. So here we have learned that some oxides are soluble in water, they form hydroxides, which are alkalis, while some oxides are partially or maybe also insoluble in water. So metal oxide can be categorized into two depending on solubility. Those that are soluble give us metal hydroxides, and these soluble are called alkalis. However, there are some that are insoluble. They do form also hydroxides, but they are insoluble in water. Now when metal hydroxide are added to litmus, we find that the red litmus turns blue. However, the blue litmus remains blue. So this clearly goes to say that metal oxides are basic in nature. So we have to remember that the nature of metallic oxides are basic. In this next reaction, we see copper oxide reacts with an acid. Hydrochloric acid is an acid to give you a salt, that is copper chloride and water. So what can you conclude about the nature of copper oxide? Is it basic or is it acidic in nature? You'll definitely say it is basic in nature. Now why basic in nature? Because it reacts with an acid. Basic substances react with acids to give salt plus water. So there's another important point we need to remember, is that metal oxides are basic in nature. Here is something interesting. We have aluminium oxide, and this aluminium oxide we know is a metal oxide. And this aluminium oxide in this first reacts with an acid to give salt and water. And in the next reaction, the same metal oxide, that is aluminium oxide, now reacts with a base, NaOH is a base, to give salt and water. And now if I were to ask you the question, what is the nature of aluminium oxide? It reacts with an acid as well as a base. Such substances are called amphoteric substances, which react both with acids as well as bases. So some metal oxides react with both acids as well as bases to give salt and water, are known as amphoteric oxides. So here the first is aluminium oxide, and when you're balancing you'll have to put here 6, 2 and 3H2O to give you sodium chloride. In this next reaction we have again aluminium oxide reacting with the base, that is sodium hydroxide, to give you sodium aluminate. So you put 2 and here is 2. You balance them out. Here is another example of a amphoteric oxide. Amphoteric oxide is an oxide that reacts with both acids as well as base, and this is zinc oxide. And if you see, zinc oxide reacts with this acid, hydrochloric acid, to give you the salt zinc chloride. It also reacts with a base. So you have zinc oxide with this base, sodium hydroxide, to give sodium zincate. And we go ahead and balance this equation. The first equation of balance, you need 2HCl here. You've got to write the form. This is aqueous, this is a liquid. I think I'll just write another letter. This is a solid, aqueous. For the next one, here again this is solid. Sodium hydroxide is aqueous, dissolved in water. Sodium zincate is also aqueous, dissolved in water, soluble in water, and this is liquid. And if you were to balance this reaction, you'll get 2 here. So zinc oxide is also amphoteric oxide because it reacts both with acid as well as base. Is amphoteric oxide, and this is the proof because it reacts with both an acid as well as a base to give salt and water. Now metals like sodium and potassium are very reactive. When they're just exposed to air, they catch fire. They act very vigorously with air. They combine with oxygen and they catch fire because they're highly reactive. Like in this picture, you can see how sodium has caught fire when just kept out in the open. So you cannot keep sodium out in the open. It has to be stored in a bottle, not just in an open bottle, but it has to be stored in kerosene. So sodium and potassium react vigorously with air. They catch fire when kept in the open. Hence they are stored in kerosene. This is very important. And when they are stored in kerosene, this cuts off the supply of air and prevents the reaction with oxygen, carbon dioxide and moisture or water. So in this picture you can see this is sodium. The symbol is Na and it is kept in kerosene. You cannot keep it in the open, it will catch fire. This kerosene cuts off the supply of air. The air now here cannot enter this bottle because of this kerosene. So sodium is unable to react with oxygen, carbon dioxide and moisture in the air. In this table we'll summarize the reactivity of metals with oxygen. When we take up sodium and potassium, they react vigorously, they catch fire when kept in the open. Then next we take magnesium, aluminium, zinc and lead. And these metals react slowly with air. They form a protective layer of an oxide. Next is copper and iron. They do not burn in air. They have to be heated, but they form an oxide layer when heated. You need to heat. When you just leave copper on outside, it does not react with air or with oxygen. It has to be heated for it. Next we have the iron filings. These are small bits of iron. They burn vigorously when sprinkled in the fire. For silver and gold, we have already discussed this. They do not react with oxygen even at high temperatures. Why aluminium articles do not corrode? Aluminium is quite a reactive metal, but its articles do not corrode. And the reason is, we have these surface atoms of aluminium, and these atoms which are on the surface of the aluminium, they react with oxygen and form a protective layer of aluminium oxide. Here, all the aluminium atoms react with the oxygen, and aluminium with oxygen gives you aluminium oxide. And because of this protective layer of aluminium oxide, the inner aluminium cannot react with the oxygen outside. This inner aluminium is unable to react with the oxygen in the air because it has got this protective layer of aluminium oxide. And that's the reason why aluminium particles do not corrode. Aluminium reacts with oxygen to form a protective layer of aluminium oxide. This cuts off the supply of air and prevents further oxidation of aluminium. So this is the layer of this protective layer which prevents further oxidation. The same case is with zinc. Zinc also forms this protective layer of zinc oxide and prevents further oxidation. So here is zinc, and it forms this protective layer outside of zinc oxide. This prevents the further oxidation of the zinc within that protective layer. Here I've done a mistake of aluminium, so I've just corrected it.